Section 9.2 deals with quadratic functions. I can graph quadratic functions of the form y equals ax squared plus bx plus c. Big ideas here. In the quadratic function y equals ax squared plus bx plus c, the value of b translates the position of the axis of symmetry. The axis of symmetry for the graphs of the quadratic function y equals ax squared plus bx plus c is x equals negative b over 2a. And this guy right here, this little formula, very important, so you're going to want to know that. That's also going to be where the x-coordinate of our vertex is on the graph, at negative b over 2a. And remember, that's because our vertex is always on our axis of symmetry. Remember, our vertex is the point where each of our branches of our quadratic stem from, and the line where the two branches would fold onto each other, that it's symmetric about, is called our axis of symmetry. If you look at the graphs on the bottom of page 553, one of them is y equals 2x squared minus 2x. And if you notice that one versus the ones that we've done before, guys, is it shifted a little bit to the left. And that's because we have this bx in our formula. The ones that we did in section 9.1 were just x squared and a constant. Here we have that bx term, and because of that b value, it shifts it left and right. And the bigger the b value, the further left and right it goes. And we can see that with our second and third graph, with the minus 4x and the minus 6x. The 2x squared stayed the same on both of those. The only thing that changed was that b value, and it shifted it further and further left and right. In example 1 here, we are going to graph this quadratic function. So because, again, we have this b value in the middle, it means that our graph is going to be shifted left and right. And we need to find our axis of symmetry before we can go any further. So x equals negative b over 2a. My b value here is the minus 6. We take the sign with the number. So minus negative 6 over 2. My a, if there's not a number in front of my x squared, guys, is a 1. Just going to give me minus minus, gives me a positive 6. It's like negative 1 times negative 6. And 2 times 1 is 2. So I'm going to get x equals 3. And this is going to be my axis of symmetry. I'm going to put a dotted line here just so I remember where it is. You don't have to. We don't need that as part of our graph, but that's just going to help me remember that that's the line where my branches would fold over each other. That's the line about which they're symmetric. Now, I'm going to go just like we did last section and make my table of values. The only difference is before, when my b value was 0 and I just had x squared plus 4, for example, we based it around 0 as the middle. We'd have like negative 2, negative 1, 0, 1, and 2. Now, I'm going to base it around 3. So the number that I get from my axis of symmetry, that's going to be my middle value. And I'm still going to pick two numbers on each side. Here I'm going to pick 2 and 1. And then 4 and 5. Again, before when we did this, it was negative 2, negative 1, 0, 1, and 2. 0 was where our axis of symmetry was. Our vertex was always on our y-axis. Now, my vertex is going to be at 3. And just like we did before with 0, where I picked two numbers on each side, I'm going to do the same thing with my 3 here. Once I have my values, I can plug them into my formula up here. So I have x squared minus 6x plus 4. Remember, these are just our x values, and they go into our formula. Here I get negative 1. X squared minus 6 times x plus 4. Minus 4. X squared minus 6 times x plus 4. Again, I'm just substituting them in for my x values here. Negative 5. X squared minus 6x plus 4. Minus 4. X squared minus 6 times x plus 4. Minus 1. And now these are our ordered pairs. So we're going to graph our ordered pairs, connect our dots, and we'll have our parabola. So at 1, -1, I have a point. At 2, -4, I have a point. At 3, -5, I have a point. At 4, -4, I have a point. And at 5, -1, I have a point. We can connect our dots. And we have our parabola. Couple things we want to check. Does our answer seem reasonable? Well, here, our x squared was positive, so we should have a happy face parabola, and we do, so that checks. If we also look, our vertex, or our minimum value here, is on x equals 3, and that's what we said was going to happen. Last thing we want to check here, guys, is that it's symmetric. So here, the same height, and the same distance away. We went 1 away, up 1, over 2, up 4, over 1, up 1, over 2, up 4. Those points are symmetric, same distance away, 4 away from my axis, 4 away from my axis. So it's symmetric, has this right vertex, and is the right direction, so it looks to be reasonable. Now, feel free to pause here and give this a try if you'd like. Again, because we have the b value here, we have to figure out where we're going to have the middle of our graph. Where are we going to base this off of? Because in our last example, our vertex wasn't until 3. So if we used -2, -1, 0, 1, and 2, we wouldn't even have seen where our graph started to curve up yet. We wouldn't have had a very good representation of our parabola. So here, we want to find where is our middle at? Where is that axis of symmetry? And in order to do that, we do -b over 2 times a. -4 over 2 times my a value here, guys. Remember, if there's not a number in front of my variable, it's a 1, and we take the sign with it, so it's a -1 there. So I get x equals 2, and that's my axis of symmetry. Again, I'm going to draw it in as a dotted line. You don't have to, but that just helps me remember that everything should be symmetric about that line. Now, once I have my axis of symmetry, I also know that's going to be the x-coordinate of my vertex. And because of that, I want that to be my middle. We know that's our highest or lowest point. Now, I pick 2 numbers on each side. So 2, 1, 0, 2, 3, 4. And I plug those into my function here for my x's. So, -0 squared plus 4 times 0 minus 2. One thing here, guys, make sure that we use exponents first and then multiplication. This is just like if I had -1 times x squared plus 4 times x minus 2. So again, make sure we use exponents first and then that multiplication with the negative. Here I'm going to get -2. Negative, and then x is squared first. So this is actually going to be -1 after we square it. Plus 4 times 1 minus 2. 1. Again, square first 4 and then make it negative. 2. One. And -2. So 0, -2. 1, 1, 2, 2. Remember, these are just ordered pairs. 3, 1, and 4, -2. Connect your dots. And there we go. Again, we want to double check, does our answer seem reasonable? Well, here we had a negative in front of our x squared, so it looks like it's going to be a sad face, which we have. We also said that our highest point then was going to be at x equals 2, which it is. And then we want to check, is it symmetric? Here and here? Yep. So our graph checks, seems reasonable, and there we go. If an object is projected into the air given an initial upward velocity v, continues with no additional force acting on it, the formula h equals -16 t squared plus vt plus c gives the approximate height above the ground. So we're going to use this formula here in the problem below. During halftime of a basketball game, a slingshot launches t-shirts at the crowd. A t-shirt is launched with an initial upward velocity of 72 feet per second. That's our initial upward velocity. The t-shirt is caught 35 feet above the court. How long will it take the t-shirt to reach its maximum height? And then what is the maximum height? What is the range of the function that models the height of the t-shirt over time? So if you look on page 555, they have a good picture of this. I have a not so great picture of this, but it's here nonetheless. So h equals negative 16 t squared plus vt plus c is our formula. And we said that our initial velocity was 72. We need to know what c is, and that's our initial height. And if we look at our picture here, and in the book it's obviously better, this is my t-shirt being ready to be launched. This is the path that it takes until it's caught here at 35 feet. Obviously not drawn to scale because this is 35 feet, and that is 5 feet. That's the person, and that's where the slingshot will let go of the shirt. So our initial height then, where the shirt starts, is right here at 5 feet. So our c value is 5. Now, we want to know how long will it take to reach the maximum height. The maximum height is about here. So we want to know from here to here, how far is that time? Well, that maximum point here is our vertex. And remember, the vertex always happens on our axis of symmetry. So x equals negative b over 2a. Here my b value is 72. My a value is negative 16. And I get 2.25 seconds. So how long will it take the t-shirt to reach its maximum height? 2.25. And that's right here. Now, we want to know what is the maximum height. So we want to know this height right here. Well, if we know our x value, we can always plug it back in just like we do with a table of values, guys. But here the only point I'm worried about right now is the 2.25, that middle point. So we're going to plug that back into our formula here. And h is going to equal 86 feet. Again, anytime we know an x value, which here is t, I guess, we can plug it back into our formula to find our y value, which here is h. So 86 feet. So the coordinates of this point right here are 2.25 and 86. Now, we want to know what is the range of the function. And our range, remember, deals with y's. Here are heights. So our height, okay, the smallest our height could ever be is 5. It gets caught at 35 feet, so it never comes back to the court. The smallest it could be is 5. And the biggest it can be is here at 86 feet. So we say that our height is in between there. Our height is greater than 5, or 5 is less than our height or equal to. Our height is also less than or equal to the 86. So again, if you wanted to, you could also use all real numbers there. All real numbers that are between 5 and 86. Now, same idea here. We're going to use the same base formula in the same situation, so same drawing. So our initial height is still 5. The only difference here is our velocity is 64. We're still going to start off with negative b over 2a. Which is going to give us 2 seconds as the x value of our maximum point. Now that we know the x, we plug it back in to find our y. And get 69 feet. And that's the maximum height. So as far as our range goes, 5 is our smallest. Our height is in between there and 69 feet. Okay, smallest height, biggest height. We use two less than inequalities there to combine them.